Welcome back to the Deep Dive. Today, we are going to do something a little different.
I think so, yeah.
Usually, we talk about the big flashy things, the user interfaces, the AI models that write poetry, the apps that are supposed to change our lives.
The stuff you can see and touch.
Exactly, the stuff on the surface.
Yeah.
But today, we are going underground. We are looking at the invisible layer of technology. We're going to talk about how software components actually speak to one another.
It's the digital nervous system, really. And frankly, it's where all the actual nitty-gritty engineering happens.
It is. And I know what you're thinking. You're probably sitting there thinking, okay, I'm not a systems architect. Why do I care about this?
Right. Why do I need to know about the plumbing?
But whether you are prepping for a system design interview, which, let's be honest, is a grueling experience for anyone, or you're just one of those people who is insanely curious about how ChatGPT seems to type out those answers so fast on your screen, this deep dive is going to peel back that curtain. We are looking at the silent, invisible conversations happening inside your computer and across the entire cloud.
It's a fascinating space because to the end user, it all just looks like magic, doesn't it? You click a button, data appears.
Instantaneously.
But under the hood, there is this incredibly complex decision-making process about how to move that data from point A to point B. And the interesting thing is it is absolutely not a one-size-fits-all situation.
No way.
The choice of how software talks depends entirely on where that software lives. Is it on your local machine? Is it distributed across data centers all over the world? And, what does it need to do? Are we trying to prioritize raw speed above everything else? Or is reliability the most important thing?
Right. It's the difference between, I don't know, sending a registered letter that will get there
Right.
versus just shouting across a crowded bar and hoping to the best.
Precisely. That's a great analogy. And in our sources today, we have what is essentially a menu of 5 distinct technologies that represent the standard toolkit for any modern architect.
Okay. We are going to cover STDIO, then SSE, gRPC, 0MQ, and finally streamable HTTP.
That is quite the alphabet soup. But I promise we're going to break it down for you. We're going to go from the absolute simplest method, we're talking literally piping text on one single computer, all the way up to these high-performance, complex distributed networks.
And just to set the stakes here, this content is specifically curated for what we call agentic and microservices architectures.
2 huge buzzwords right now.
Huge, but for good reason.
Okay.
These are the fundamental building blocks of modern AI and cloud systems. So if you want to understand how the next generation of software is being built, you have to understand these 5 conversational styles. It's not optional anymore.
Okay, let's get into it. Let's unpack this. We're starting with the local connector, the simplest of the simple, STDIO.
Back to basics.
It is. And I have to be honest with you, when I see standard input-output on a modern architecture diagram, my first instinct is, are we writing a bash script in 1998? It feels incredibly archaic for something like a modern AI agent. It feels that way, doesn't it? It has that sort of retro command line vibe. It feels like we're going back to the Stone Age of computing before we had all these fancy network protocols.
Yeah.
But you have to look at where the complexity lives. If you're using HTTP or some other web protocol, all the complexity is in the network stack. You've got headers, TCP handshakes, ports, routing tables, firewalls.
So much overhead.
So much. With STDIO, you're stripping all of that away. You are effectively connecting 2 processes directly via the operating system's kernel. It's the most direct path you can possibly have.
Okay, so walk us through the mechanics here. I know what it looks like in my terminal when I pipe one command to another, but what's actually happening in the system?
So STDIO stands for Standard Input-Output. It refers to the 3 standard streams. You have standard in, which is std-in, standard out, std-in, and standard error. Stutter.
The holy trinity of the command line.
Exactly. And these are available to virtually every single executable process on a computer.
Virtually every executable. That's a bold claim.
Well, it's the bedrock of how modern operating systems work. If you can run a program on Linux, Windows, or a Mac, it has these 3 streams attached to it. It's fundamental.
Okay.
And the mechanics usually follow a parent-child relationship. You have a main program, let's call it the client or the parent, and its job is to spawn a subprocess.
The child.
The child, the server, they are inextricably linked. They're sitting right next to each other in the system's memory space, effectively.
So the analogy that came to mind when I was reading about this is like passing notes in class.
That's a common analogy, yes. It gets the point across.
You have 2 people sitting at the same desk. They aren't shouting across the room. They aren't using a walkie-talkie or sending a text message. They're just sliding a piece of paper back and forth silently.
It works as a visual, but technically it's even more intimate than that. It's more like they are sharing a brainstem.
Whoa.
Because the parent process, the client, writes messages, usually formatted as JSON, directly into the server's STEN. That's like whispering directly into the server's ear. And then it listens for the response by reading from the server's Stitout, which is the server's mouth. It's a very direct, private conversation.
But here's where I start to get a little bit skeptical.
Yeah.
You say it's effective, but if we were just piping raw text, isn't that incredibly fragile?
Yes.
I mean, we aren't using a structured protocol with, headers and error checking. If one character is off, if there's a typo in the JSON, doesn't the whole thing just break?
You are hitting on the biggest trade-off right out of the gate. Yes, it can be incredibly brittle, specifically when it comes to message framing.
Framing. What do you mean by framing?
A pipe is just a stream of bytes. It's a continuous flow. The operating system doesn't know where one of your JSON messages ends and the next one begins.
It's just a fire hose of text. There are no dividers.
Exactly. So if your agent process crashes halfway through writing a JSON object, your listening process on the other end just gets a chunk of malformed text, like a half-open curly bracket and a quote, and it just chokes.
And there's no recovery.
Not automatically. You don't have HTTP status codes like 400 bad requests to save you. There's no built-in mechanism to say, hey, that last message was garbage, can you send it again? You have to build that reliability layer on top of it yourself.
So why do it? I mean, that sounds like a lot of work and a lot of risk. Why not just spin up a little local server on port 3000 and talk to it like a civilized human being with a REST API?
2 words. The first is performance. The second, and arguably more important one, is security.
Let's start with performance. You call it zero network overhead. What does that really mean in practice?
It means we're not packaging data into PCP packets. We're not doing a DNS lookup for localhost. We're not negotiating a 3-way handshake. We're not creating sockets and binding them to ports. All of that disappears.
It's a direct memory copy, basically.
It's as close as you can get. The OS kernel is just moving bytes from one process's buffer to another's. It is blisteringly fast. For high-frequency, local communication, it's unbeatable.
Okay, that's compelling. But talk to me about the security angle. That seems even more critical.
Think about the Model Context Protocol, or MCP, which is mentioned in the source material. It's a protocol for AI agents. Now, imagine you have a local AI agent running on your laptop.
Okay.
And this agent needs to do something sensitive, like read a file from your desktop or access a local database full of your personal information. Do you really want that data leaving your machine even for a millisecond?
Absolutely not. No way.
And do you really want to open a network port? Because if you open port 3000, even if you bind it to localhost, you are technically exposing a listening interface.
Right. Something can connect to it.
Yes. If you have some other piece of malware on your machine, or if you're on a compromised network with some weird DNS or routing rules, that port becomes an attack vector. It's a tiny little open door into your application.
Ah, I see. So by using STDIO, you are basically air-gapping the conversation from the network.
Exactly. That is the perfect term for it. There are no ports involved. There are no IP addresses to look up. There is no Wi-Fi handshake. The data never gets packaged to be sent out to a router and back. It never, ever leaves the machine.
So it's completely invisible to the outside world.
Completely. It is the safest possible way to communicate with a local sidecar or helper agent because the communication channel is entirely internal to the OS.
That makes a ton of sense. So if I'm building a super secure application or something that handles very private data, I might want to keep things on STDIO just for that reason alone.
You'd strongly consider it, yes.
But where does this fit architecturally? I assume I'm not using this to run a distributed social network.
No, absolutely not. You'd never use this between 2 different machines. This is architecturally ideal for local. Imagine you have a command line interface, tool, a CLI. Or maybe a desktop application like a code editor. And that app needs to talk to a local script to perform a specific task, maybe linting your code or analyzing a log file or running some kind of calculation.
Right.
You don't need a whole web server for that. That's massive overkill. You just spawn the script as a subprocess, talk to it via STDIO, get the result, and then the subprocess dies. Clean, efficient, and secure.
It's basically the plumbing for this new wave of desktop AI and developer tools.
Correct. It's unglamorous. It requires you to write your own error handling and message framing. But for what it does, it is faster and more secure than any other option.
Okay, so that's the local conversation.
Mm-hmm.
Passing notes at the same desk, sharing a brainstem, very intimate, very private.
Yep.
But now, let's zoom out. What happens when we need to leave the desk? What happens when we have to move this conversation to the web?
That is where we encounter our second technology. This is where things get a bit more complex, but also more familiar to most web developers. We're talking about SSE.
Server-sent events,
Mhm.
or as the outline calls it, the one-way broadcaster.
A very fitting name.
Now, I have to admit, I've been burned by this before. Everyone I talk to, every blog post I read says, oh, SSE is just easy WebSockets. But it's not just easy WebSockets, is it? There are traps.
Laughs.
Yeah.
No, it is definitely not. And if you go into it with that mindset, thinking it's a drop-in replacement, you are going to have a very bad time and a very long night of debugging.
Been there. So let's define it properly first. What is SSE?
So SSE is a standard that allows a server to push data to a client over a single long-lived HTTP connection.
Long-lived being the really key phrase there.
Yes. Normally, HTTP is what we call transactional. You, the client, make a request for a page. The server finds it, gives it to you, and the connection closes. It's a handshake and a goodbye. Very polite, very final.
Get in, get the data, get out.
Exactly. But with SSE, the client opens a standard HTTP connection, and the server says, okay, I acknowledge your request, but I'm going to keep this line open. Don't hang up.
It leaves the phone off the hook.
Right. And then whenever the server has new information to share, a new notification, a status update, whatever, it just sends these little text-based events down that open line to the client.
But the source calls this unidirectional.
Yes, and that is the single most critical distinction to understand. It is designed primarily for server-to-client communication. The server talks, the client listens. It's a monologue, not a dialogue.
So if the client wants to talk back, if I'm on the web page, I want to send a message to the server.
It can't. Not through that same SSE connection.
Really? Not at all. There's no way to sneak a message back up the pipe.
Not directly on that pipe, no. The SSE channel is a one-way street. However, in practice, what you do is you pair it with standard HTTP POST requests.
Ah, so you use two different channels.
Exactly. You have the SSE stream for all your incoming updates from the server, and then when the user clicks a button, you fire off a separate normal POST request for any outgoing commands or data. It's a hybrid approach.
Okay, that clarifies things. Now let's get back to why I've been burned by this. The dreaded browser connection limit.
Ah, yes. The classic trap. A rite of passage for any SSE developer.
For our listeners who haven't spent until 3 a.m. debugging this exact issue, browsers have a hard limit on how many simultaneous connections you can have open to a single domain.
It's usually 6. That is the hard limit in Chrome, Firefox, most modern browsers. 6 connections per domain, not per tab, per domain.
All right, so imagine I'm building a dashboard, a financial dashboard. I want 10 different widgets on the screen, and each widget needs to connect to the server to get real-time stock price updates. I decide to be clever and give each widget its own SSE stream for simplicity.
And you have just unintentionally brick your application for any user who loads it.
Because the first 6 widgets load perfectly.
And they each consume one of those 6 available connection slots. And the 7th, 8th, 9th, and 10th widgets, they just sit there with a spinner forever.
They're waiting in line for a slot to open up, but since SSE connections are long-lived, a slot never does. And the user just thinks the site is broken.
It's a nightmare scenario because it fails silently. There's no big error message. It just hangs.
So why use SSE if it has this pretty severe limitation? Why not just use WebSockets for everything? WebSockets are fully bidirectional. They are well-established. They seem more robust on the surface.
It comes down to simplicity and infrastructure. The expert source puts it bluntly. It's just HTTP.
Simplicity wins. Again.
In the web world, often, yes. WebSockets are a completely different protocol. They start out looking like an HTTP request, but then there's this special upgrade handshake.
Right, the upgrade, WebSocket header.
Exactly. And that upgrade can be a total nightmare for older corporate firewalls, proxies, and some load balancers.
The firewall sees this weird traffic that isn't standard web traffic and thinks, I don't know what this is. I'm just going to block it to be safe.
Precisely. But SSE, it just looks like a web page that is taking a really, really long time to load. To a firewall, it's just a standard, open HTTP GET request, it flies completely under the radar.
That's a huge operational advantage.
It is. Plus, it has resilience kind of built in. Most browser clients, if the SSE connection drops for a second, will handle the reconnection automatically. They'll even send the ID of the last event they received so the server can catch them up.
Oh, that's nice.
With WebSockets, you have to write all of that retry logic and state management yourself. And that's not trivial.
Yeah, I'd rather not write custom retry logic if I don't have to.
And the data itself, what does it actually look like coming down that pipe?
It's just plain text, right? Usually the events are prefixed with data.
Right. It's a very specific wire format. You have to prefix everything with data. So a message would look like data, user, Steve, action, login, followed by 2 new lines.
That double new line is the trigger, isn't it?
It is. It's the end of message marker. If you forget that, the browser just sits there buffering, waiting for the message to end, and you'll pull your hair out trying to figure out why nothing is showing up.
So where does this fit in our overall architecture?
Well, the source notes that it's the standard transport for remote agents in protocols like MCP. But the perfect use case, and the one that listeners will immediately recognize, is streaming LLM tokens.
LLM tokens, you mean from large language models like the ones that power chatbots?
Exactly. When a server agent needs to send a status update back to a client, or, more importantly, stream a generated response word by word, SSE is often the vehicle of choice. It pushes the information to you as it happens.
Okay, hold on. This sounds very, very similar to something else in our stack today. We have SSE, the one-way broadcaster. But the next item on our menu is streamable HTTP.
The pragmatic streamer.
Right. And looking at the notes here, the host, that's me, is supposed to ask, how is this actually different from SSE? Because they both seem to involve the server sending data to the client over time on a single connection.
It is a very subtle but incredibly important distinction. SSE is a specific browser API and protocol specification. It has that rigid format we just talked about, the data prefix, and the double new line. It has built-in browser support with the event source object.
The formal standard.
A formal standard. Streamable HTTP, on the other hand, refers to a more general practice or technique.
A practice, not a protocol.
Correct. It's not a new protocol. It refers to the underlying mechanism of sending data incrementally via a standard HTTP 1.1 feature called chunked transfer encoding.
Okay, chunked transfer encoding. Let's break that down because that sounds like deep network jargon.
It is, but it's actually pretty cool once you get it. When you normally download a file, say an image, the server tells your browser in the response headers, hey, content length, 50,000. It tells you up front this file is 50 kilobytes.
Right. It knows what to expect. Your browser shows a progress bar.
But with chunked transfer, the server sends a different header. It sends transfer encoding, chunked. And what that's essentially saying is, I don't know how long this message is going to be yet. I haven't finished generating it.
It's like saying, I'm just going to start talking and I'll tell you when I'm done.
Exactly. Here's a chunk. Here's another check. Okay, here's the final chunk, and now I'm done. The server sends these pieces of data as they are generated without needing to know the total size in advance.
And the format of those chunks. Can it be anything?
It can be anything, but a very common format mentioned in our source is NDJSON, which stands for New Line Delimited JSON.
Which means?
Simply that every single line of text in the stream is a valid standalone JSON object. You don't have to wait for a giant closing bracket at the end of a massive file. You can just read the response line by line, parse each line as JSON, and process it immediately.
Got it. So why do we care about this distinction? Where is the real aha moment here?
The aha moment is the entire generative AI experience that we've all become used to. Think about ChatGPT.
Okay, I'm with you.
When you ask it a question, do you sit there and wait for 10 seconds staring at a blank screen, and then suddenly the entire 3-paragraph essay appears all at once?
No, of course not. It types it out. It looks like a ghost is typing on my screen. It's actually kind of mesmerizing to watch.
That effect, that magical real-time typing, that is streamable HTTP using chunked transfer encoding.
So ChatGPT is essentially chunking its response to me.
Exactly. It is the absolute backbone of the modern generative AI web stack. The underlying model generates the answer one token, which is like a word or part of a word at a time. Instead of waiting for the whole thought to be finished, the server wraps that single token in a chunk and sends it immediately to your browser.
So my browser gets the first word, displays it, then gets the second word, displays it, and so on.
Precisely. This allows you to start reading the beginning of the sentence while the AI is still figuring out how the sentence is going to end.
That's a profound shift in user experience.
It's everything. It's about time to first byte versus time to total completion. The total time to generate the full answer might be the exact same, say 5 seconds. But because you see the first word in 200 milliseconds, your brain perceives the response as instant.
Whereas if you waited the full 5 seconds staring at a spinner, you'd assume the server was slow or had hum.
You get frustrated and maybe even close the tab. It changes the user experience from loading to interacting. That is huge.
Sure.
It really is the difference between a frustrating lag and what feels like a magical live conversation.
It really is.
Yeah.
And it all relies on this pragmatic approach of just sending what you have when you have it.
That's it.
Okay, so we've covered a lot. We have STDIO for passing local notes. We have SSE for specific one-way server alerts. And we have streamable HTTP for that interactive typing effect in AI. But now we need to get serious. We are leaving the world of browsers and text. We are entering the enterprise data center.
We're going to where the heavy machinery lives.
Section 4, the high-performance specialist, gRPC.
Google Remote Procedure Call.
Now, remote procedure call sounds like something from the 90s.
Yeah.
I have these vague, unpleasant memories of things like Corba and SOAP and these complex XML schemas.
It definitely shares some DNA with those older technologies. The concept of RPC is old. The idea of making a function call on a remote server look and feel exactly like a local function call in your code. But gRPC is the modern, supercharged evolution of that idea. It's an open source framework, originally from Google, that uses HTTP2 for transport and something called protocol buffers for serialization.
Okay, that's a lot of jargon right there. Let's unpack that. First, HTTP2. How is that different from the plain old HTTP we just talked about with SSE and chunking?
HTTP2 is a major upgrade to the protocol. The biggest feature it brings to the table for us is that it allows for a single, persistent connection that supports true bidirectional streaming and multiplexing.
Multiplexing is one of those words that makes you sound smart at parties. But what does it actually mean in this context?
Laughs. It's a good one to have in your back pocket. Imagine a highway. In HTTP 1.1, you basically have one lane. You send a car, it delivers a package, and it has to drive all the way back before you can send the next car.
So stop-and-go traffic. A request has to finish before the next one can start on that connection.
Exactly. In HTTP 2, you have a multi-lane superhighway. You can have dozens of cars going back and forth simultaneously, weaving around each other, carrying different payloads for different requests, all on the same single road, the same TCP connection.
So the client and the server can both be talking at the exact same time on multiple streams.
Simultaneously. It's incredibly efficient for chatty applications. And then you add the second part of the magic formula, protobuf.
Protocol buffers.
Right. So far, everything we have discussed, STDIO, SSE, streamable HTTP, it all uses text, usually JSON. And text is great for us humans because we can read it. You can open up a log file and see name, Steve.
It's debuggable.
It's very debuggable. But text is heavy and inefficient for a computer. It takes up a lot of space.
And computers don't need to read it like we do.
Exactly. And this is where the real engineering grit comes in. To parse a JSON string, a CPU has to work surprisingly hard. It has to scan every single character, look for opening brackets, closing brackets, commas, quotes, handle escape characters.
It's computationally expensive just to figure out what the data even is before you can use it.
Correct. gRPC, on the other hand, uses binary serialization with protocol buffers. It turns that data into a tight, compact, binary code that a computer can understand natively.
Okay, give me a sense of the scale here. How much more efficient is it?
Well, the payload size is much smaller. For example, the number 1,000,000 in JSON is 7 bytes of characters, 10000000. In a binary format like protobuf, a 32-bit integer is always just 4 bytes.
Okay, so that cuts the size nearly in half right there. And over millions of requests, that adds up.
It adds up massively.
Yeah.
And, crucially, it is much, much faster for a computer to parse. With protobufs, the format is predefined. The computer knows that, for example, byte 4 to byte 8 of this message is the user ID, and it's an integer. There's no scanning required. It's a direct memory mapping.
So gRPC is strictly defined and incredibly fast. It sounds amazing. But if it's so good, why aren't we using it for everything? Why are we still messing around with JSON and REST APIs for our public-facing websites?
Because of the contract.
A .proto file.
Yes. In gRPC, you have to define a strict service contract using a .proto file. This file is the single source of truth. It says, the create user function expects exactly this type of data in this order with these data types. If you break that contract, the system rejects it.
There's no room for error, no optional fields unless you explicitly define them.
Zero ambiguity. But that creates what we call strict or tight coupling between the client and the server.
Ah, the classic coupling problem.
If you on the server team decide to change a field, maybe rename it or change its type, and you don't update the client team with the new .proto file, their application breaks. Hard.
And to use your service, I have to have your .proto file.
You must. You use that file to auto-generate the client code in whatever language you're using, which is great, but it means you have to distribute that .proto file to everyone who wants to talk to you.
Which is perfectly fine if everyone is your own team inside your own company.
Yeah.
You just put it in a shared repository.
Exactly. That's why gRPC is the king of east-west traffic.
East-west. Explain that.
In system architecture, north-south traffic is traffic coming from the outside world into your data center, like a user on a web browser talking to your server.
Okay.
East-west traffic is all the communication happening between your servers inside the data center.
Ah, server-to-server communication.
Right. And gRPC is absolutely dominant for internal microservices, where low latency is the most critical factor. If you have 50 different microservices that all need to talk to each other to process a single credit card transaction, you need them to whisper to each other instantly. You use gRPC for that.
But you wouldn't typically use it for your public API that you want thousands of developers to use.
It's much less common. The friction of managing that .proto file distribution and versioning with the general public is a nightmare. It's like trying to get a million strangers to agree on a secret handshake and then changing it every week. For public APIs, the flexibility of JSON and REST is usually worth the performance hit.
Got it. Okay. So gRPC is the disciplined, high-speed corporate suit. It's efficient, it's strict, it's binary. But now we get to the wild card, the maverick of the group.
Section 5. The brokerless messenger. 0MQ or EMQ.
0MQ. Even the name sounds cool. The description here says it looks like a socket library but acts like a concurrency framework. What on earth does that mean?
It's a truly fascinating piece of technology, and it breaks a lot of the rules we take for granted. So if you are familiar with message queues like RabbitMQ or Kafka, you know they usually rely on a big central server, a piece of software we call a broker, to manage all the traffic.
Right. It's the traffic cop in the middle of the intersection directing all the cars.
Exactly. The broker provides safety and durability. If the receiver of a message goes down, the broker holds on to that message until the receiver comes back online. It guarantees delivery.
It's like the post office. They hold your mail for you if you're on vacation.
A perfect analogy. 0MQ comes along and asks the fundamental question, what if we fired the traffic cop?
Chaos. Anarchy.
Organized chaos, maybe. 0MQ is brokerless. It does not require a centralized server at all. It is just a library that you link into your application code.
So wait, hold on. If there is no central broker, where does the message queue live? Where are the messages stored while they wait to be processed?
That is the million-dollar question, and the answer is what makes 0MQ so different. The queue lives in the memory, the RAM of the sender, and the receiver processes themselves.
Whoa. So if my process crashes,
The data in its queue is gone. Poof.
that seems like a massive, terrifying trade-off. Why would I ever accept that risk of losing data?
For two reasons: extreme speed and topological flexibility. If you are building, say, a high-frequency trading bot or a real-time sensor array for a scientific instrument, you cannot afford the latency of sending a message to a central broker and then waiting for it to be routed back.
Every nanosecond counts.
Every single one. You want to talk directly to the other machine, peer-to-peer. And there's also a different kind of resilience. If your central RabbitMQ cluster goes down, your entire architecture grinds to a halt. It's a massive single point of failure.
Right.
With 0MQ, there is no central master. There's no single point of failure to take down.
So it's fully decentralized.
Completely. And what the library does is it gives your normal network sockets superpowers.
Superpowers.
Normally, dealing with raw TCP sockets is really hard. You have to manually handle disconnects, you have to manage buffers, you have to write retry logic. It's painful. 0MQ handles all of that background noise for you. It does automatic reconnection. It handles in-memory queuing. It does message framing all automatically.
So it makes the difficult parts of networking easy, but without forcing you to use a central boss.
You got it. And because of this, it allows you to build incredibly complex and sophisticated network topologies that would be very difficult otherwise. The source mentions patterns like REQ, REP, which is a simple request reply.
Standard client server.
Yep. Then there's PubSub, publish subscribe, where one process can broadcast messages to many listeners, and Pucci-esh HBUL, which is for building pipelines of work.
I love the name push-pull.
But the real architectural fit here, the killer use case, is mesh networking.
A mesh of interconnected agents.
Imagine you have hundreds of AI agents or IoT devices deployed in the field. You don't want them all reporting back to one single master server. That's a huge bottleneck and a single point of failure. With ZeroMQ, they can talk directly to each other in a peer-to-peer mesh.
So one agent can farm out a task to 50 other agents and then collect the results.
That's the fan-out, fan-in pattern. It's a classic distributed computing pattern. You send a job to multiple workers in parallel, that's the fan-out, and then you collect all the answers, that's the fan-in. ZeroMQ handles the complex routing for that dance without you needing to install and manage a massive Kafka cluster. It is the closest we can get to bare metal networking performance while still having a smart library handle all the messy TCP handshakes for you.
Wow. Okay, we have covered a lot of ground. I feel like we've been on a full tour. We've been local in the kernel. We've been on the public web. We've been deep inside a corporate data center. And now we're out in a distributed mesh network.
It's a full tour of the invisible landscape of modern software.
So let's bring it all together. This is section 6, synthesis and strategy. We need a cheat sheet. I'm going to throw a few common scenarios at you, and you tell me which tool from our menu we should pull out of the toolbox.
All right, let's do it. Rapid fire.
Scenario 1. I am building a private local desktop app, maybe a developer tool. I need to run a Python script securely on the user's machine to analyze some code, and it needs to be fast and totally private.
STDIO, no question. It uses inter-process communication pipes, it can handle text or JSON, and it has absolutely zero network overhead. It's the secure, fast, local choice. Just remember, you have to handle your own error parsing and message framing.
Okay, scenario 2. I have a server that needs to send simple, infrequent status updates to a web browser. Things like, your video encode is started, it's 50% complete, job finished.
SSE, server sent events. It's lightweight, it's firewall friendly because it's just HTTP, and it's perfect for those one-way notifications. Just be very careful about that 6 connection per domain browser limit. Don't open too many.
Scenario 3. I am building the next ChatGPT killer. The user experience is everything. I need that magical typing interface where the answers appear on screen word by word as they are generated.
Streamable HTTP, specifically using chunked transfer encoding with something like ND-JSON. You want that immediate feedback loop for the user. It's all about perceived performance, not necessarily total time.
Scenario 4. I am working at a massive tech company. We have 500 different microservices running inside our cloud that need to trade data with each other constantly. Latency is money. It has to be instant.
gRPC, hands down. You need the binary speed of protocol buffers and the parallel streaming and multiplexing of HTTP2. It's the high-performance specialist for internal traffic. You pay the price in strict contracts and coupling, but you gain massive efficiency.
And finally, scenario 5. I'm building a decentralized network of autonomous robots or financial trading agents. They need to coordinate with each other in real time without a central commander that could fail.
ZeroMQ, the brokerless messenger. It gives you the power and flexibility to build a resilient, high-performance mesh network without a single point of failure. But you trade durability for that speed. If a node dies, its in-memory messages are gone.
Man, when you lay it out like that, it really does feel like a well-defined toolkit. There's a clear reason for each one to exist.
That's the goal. A good architect doesn't have a favorite tool, they have the right tool for the job. And knowing which job requires which tool is half the battle.
So we've synthesized the knowledge, we've created the cheat sheet. But we always like to leave our listeners with something extra, a final provocative thought to chew on.
I was looking at the very end of our source material, and it poses this really interesting implementation challenge. It asks a simple question. What happens when we mix these?
A hybrid, like connecting one type to another.
Exactly. Imagine you're building a system. On one side, you have a highly secure, local AI agent running on a private server in a data center. It's communicating with its core model via STDIO, totally air-gapped from the network, totally private, super fast.
Okay, the secure core.
On the other side, you have a user on their laptop in a coffee shop using your web app. They're connected to your web server via SSE to get live updates.
So you have to somehow translate that local private pipe into a global web stream.
Precisely. How do you build a bridge? How do you take the raw, unstructured byte stream output from a local process, which has no concept of the web, of HTTP, of anything, and pipe it seamlessly and safely into a global HTTP stream that's being pushed to thousands of users?
That's the missing link, isn't it? That's a really hard engineering challenge. You have to handle back pressure, error translation, security.
That is where the future of hybrid agent architectures lies. We aren't going to live in a world where everything is just local or everything is just cloud. The future is connecting that secure, high-speed, local brain to the distributed, accessible web interface. Building that bridge is the next great challenge.
It really challenges the way you visualize the screen. You look at a simple chat window now, and you don't just see text appearing.
No. You see a gRPC call firing in the cloud to a coordinator service, which then spins up a worker node, which in turn starts a streamable HTTP chunked response back to the browser, which then parses and renders it. All while a local STDIO sidecar is logging the analytics securely to disk.
It's a symphony of invisible conversations.
It is. And if just one of those instruments is out of tune, if you use the wrong protocol for the job, if you use polling instead of streaming, or text-based JSON instead of binary protobufs in a hot path, the whole experience falls flat and feels slow and clunky.
Well, there you have it. We've gone from simple text pipes running on one machine to complex, decentralized, distributed meshes. The invisible layer turns out to be arguably the most critical part of modern system design.
If the data can't move efficiently and reliably, the system is dead. It's really that simple.
So here is our challenge to you, the listener. The next time you're using an application, look at what it's doing. Look at the software you use every day. Try to identify which of these 5 technologies might be doing the heavy lifting under the hood. Is it passing notes? Is it broadcasting? Is it streaming chunks? Once you start seeing these invisible conversations, I promise you, you can't unsee them.
It completely changes how you look at the screen in front of you.
Thanks for diving deep with us today. We will see you on the next one.
See you then.